Hafnium isomers, atomic nuclei pumped up on steroids and ready to explode like overinflated balloons at a kid's birthday party. These beefed up atoms pack an astounding amount of energy tightly coiled up inside their tiny nuclei, just waiting for the right poke to unleash their pent-up power. But what exactly is this microscopic stick of dynamite? Hafnium isomers are forms of the metal hafnium, in which the nucleus has the same number of protons and neutrons, but the energy stored in the nucleus is cranked up to insane levels. The nucleus acts like a tightly compressed spring under huge tension and just looking for any excuse to violently unwind. The most promising isomer is Hafnium-178m2, packing 2.5 million electron volts of nuclear energy in each atom, about the same as a mosquito hitting your arm at 600 miles per hour. Youch! With that much zip locked up, hafnium isomers have more spark than plutonium atoms dosed up on radioactive Red Bull. Now the trillion-dollar question: can we get these pumped up nuclei to actually detonate and release all that juicy energy? Easier said than done. Isomer experts are more divided than fans of Beatles versus Rolling Stones. What's your pick? In 1998, Carl Collins claimed that popping hafnium with X-rays from a second-hand dental X-ray machine caused it to decay faster, releasing energy. But others attempting the same thing came up empty-handed, unable to reproduce his results. Collins blamed shoddy experimental design, but skeptics smelled fishy, like when my cousin claimed his dog ate his homework. This controversy has the scientific community more fired up than the feud between Edison and Tesla over AC versus DC power. If scientists could finally tame these tiny nuclear firecrackers, hafnium isomers could power mind-blowing innovations that make sci-fi look tame. Picture packing the punch of a kiloton of TNT into an atomic hand grenade, the holy hand grenade. Just 1 gram of hafnium would deliver a kaboom to make Wile E. Coyote jealous. Hafnium-fueled engines could rocket us to Mars faster than Jeff Bezos in a midlife crisis. Just a pinch of this purified isomer weighs less than a bag of popcorn, but it could send Marty McFly back to the future 100 times over. But harvesting atomic energy is trickier than getting teenagers off TikTok. It requires ultra-precise photon beams tuned to perfection, kind of like a karate chop triggering a barrel of nuclear dynamite. Even with blown budgets and bruised egos, scientists persist in coaxing these finicky atoms to unlock their energy. Success would be more rewarding than Iron Man and Hulk teaming up to smash the bad guys. It would quite literally change the face of the Earth. The heroes of this atomic adventure could form their very own scientific Avengers. Leading of the pack is Carl Collins, convinced his dental X-ray toy could pop the lid off hafnium atoms like a can of whoop-ass. Arch nemesis Peter Zimmerman slammed this as very bad science, and them's fighting words. But Collins retaliated, calling critics brainless as zombies from The Walking Dead. The atomic arena sees more thrills and spills than WWE wrestling. But will Collins go down in history as the maestro of super hafnium, or will Zimmerman save science from misguided research? Meanwhile, a wild Eshin Khan enters the chat, hyping isomers as the power source of the future. Despite the naysayers, his faith remains as unshakable as Obi-Wan Kenobi's belief in the Force. And so, the drama intensifies. Rivalries wage, critics circle, hype and hope collide in the quest to unleash atomic fury. But hafnium's secrets remain locked away, for now. But with brash thinkers like Collins, the day of reckoning inches closer and closer when nuclei will reveal their hidden force. So what exactly is causing all this atomic angst? Why is triggering hafnium's power proving to be so difficult? It comes down to the physics. Releasing nuclear energy requires ultra-precise high-energy photons to kick the atoms in just the right way. We simply can't generate the perfectly tuned photon beams needed to unleash the isomer's fury. It's like trying to shoot an apple off someone's head blindfolded. Extremely hard and not recommended for amateurs. Collins tried zapping hafnium with his second-hand dental X-ray machine, claiming moderate success, but duplicating his results are proving difficult or impossible, probably because the photon energy was way off target, like trying to open a lock with a wet noodle. Other key experiments ended in heartbreak. The infamous trip test at the Brookhaven synchrotron was supposed to conclusively resolve the debate, but the results were classified as top secret, perhaps to hide the embarrassing failure, or maybe success, who knows? So the saga continues. Could artificial intelligence and machine learning algorithms crack the problem? Perhaps an AI system could rapidly analyze millions of possibilities and determine the precise photon beam parameters needed. But then again, AI can sometimes be dumber than my fish who keep bumping into the glass and eating their own poop. I wouldn't trust an AI system not to blow up the lab by mistake. Before racing off to build Hafnium power hoverboards, let's note that real-world applications are still pretty far off. The physics of triggering the isomer's energy remains bewilderingly complex, and after decades of research, the experts are still baffled, like cricketers trying to decipher the rules of baseball. Even if we could harness the power, the cost would be astronomical, like buying a Ferrari just to drive to the grocery store. By one estimate, it costs over $1 million just to store 1 joule of energy in a hafnium nuclei, the world's most expensive AAA battery. So while the visionaries continue sharing the dream, we should remember that this research is driven by scientific curiosity, not weapons development. But you can bet your bottom dollar that weaponizing hafnium isomers was intensely studied. As recent as the early 2000s, there was interest in weaponizing hafnium isomers. The idea was that gamma rays emitted by the decaying isomer could be used to kill or incapacitate its target. But there are a number of problems with this idea. First, the energy density of hafnium isomers is relatively low, which means that a large amount of hafnium isomer is needed to make a weapon that is small and portable enough to be practical in any sense. In other words, it's possible, but it would have to be really big. The exact size of a weapon using hafnium depends on a couple of factors, like the desired power yield and the efficiency of the shielding, because remember, these babies are nuclear. A hafnium-packed weapon with a yield of 1 kiloton needs about 100 kilograms of hafnium. For comparison, a nuclear bomb with a yield also of 1 kiloton requires only about 2 kilograms of plutonium or uranium. So a hafnium isomer weapon would have to be about 50 times larger than a nuclear bomb of the same yield. So based on these figures, a hafnium bomb would have to be about the size of a semi-truck or even a small building. Not really practical. Then there's the gamma rays emitted by hafnium isomers, which are very penetrating. That makes them extremely difficult to shield from the radiation, and they would create a massive risk to anyone working with them. Considering all of these factors, the efficiency of the energy produced from hafnium isomers is about 1%, whereas plutonium or uranium is about 20%, and you need a heck of a lot more hafnium to make it work. The mysteries of these atomic nuclei are still slowly unfolding. Perhaps one day there will be a viable use for them. If money grew on trees, I'd love to see what a new generation of scientists could discover if freed to follow their passions. Perhaps they would uncover isomer secrets, hinting at new realms of physics like Einstein realizing that time slows at high speeds. Rather than fueling destruction, maybe hafnium isomers could energize creative innovations that save lives instead of sending them. The same physics that could power the holy hand grenade could also empower medical implants to monitor health and selectively destroy tumors with surgical precision. Miniaturized isomer devices could be implanted to deliver highly targeted doses of radiation to cancer cells, while avoiding damage to surrounding tissue. We could fight disease by harnessing atomic abilities, rather than unleashing atomic horrors. Beyond fighting cancer, micro-isomer power sources could enable all kinds of medical marvels. Imagine swarms of microbots powered by isomers, patrolling our bloodstream, filtering toxins, and keeping cancerous cells in check, or even your cholesterol. Or what about isomer-charged brain implants fine-tuned to monitor neural activity and stimulate specific regions, helping to restore motor skills after trauma or disease? We've only just begun to scratch the surface of the potential healing applications of these bad boys. The mere act of discovery also has value. Pushing the boundaries of knowledge is a fundamental human pursuit that lifts our species. Even if practical applications are proving elusive, unraveling the secrets of hafnium isomers expands our understanding of the quantum realm. Pure science need not be justified by practical spin-offs. The act of exploration is worthwhile itself. Though the road is long, the journey of discovery will continue. Of course, we can't force nature's secrets from her grasp. The truth emerges in its own time. But the human impulse to learn is unstoppable. Whether masters or students, we will keep searching. We will keep trying new approaches and asking new questions. Thanks for watching.